We're going to continue to work with complex numbers, and particularly we're going to be looking at DeMoivres theorem. It's a way to expand or raise complex numbers to powers like second degree, third degree, fourth degree powers, and then also to find roots as well. So first of all, let's go ahead and get DeMoivres theorem down, and again, this will be a nice one for your note card. And we're going to use the same idea for the roots, so we're going to kind of be using this twice. So DeMoivres theorem basically says is if you have a complex number, and remember we have different forms of complex numbers. We have the rectangular form, and then we also have what we're writing down here is the trigonometric or the polar form, raised to some power of n. Instead of expanding that out and multiplying it and foiling it like we're used to doing, DeMoivres theorem says this is just equal to r to the n. So I'm taking this n and distributing it to the r times the cosine of n theta plus I sine of n theta. So that's DeMoivres theorem, and it's kind of hard to understand until we look at some examples, so I think that's the first thing that I would like to do is to look at some examples. Now if we had a problem, and this will be familiar to you, something like a complex number negative 2 plus 2i root 3, and we wanted to square that, what I would have to do is I would have to remember, first of all, I can't take the 2 and distribute it through. I actually have to multiply this by itself, and I can use the FOIL method or the box method here. Doesn't matter to me which one. I'm going to go ahead and use the FOIL method. So here's my first terms. Here's my outside terms. Here's my inside terms. And here's my last terms. 2i root 3, 2i root 3. And now we're going to simplify. Negative 2 times negative 2 is 4. Minus 4i root 3 from here. Another minus 4i root 3. Then my last term is a positive. Okay, I have 2 times 2 is 4. I times I is I squared. And then root 3 times root 3 would be root 9, which will eventually change to a 3 here in a moment. So continuing to simplify, I have 4 minus 8i root 3. And then I have plus 4. I squared is negative 1 times 3. 4 times 3 is 12, times negative 1 is negative 12. 4 minus 12 is negative 8. So this is negative 8 minus 8i root 3. Okay, so that's not bad. That's not a bad problem to work through. We know how to FOIL. We're just throwing in complex numbers now. Now what DeMoivres theorem says is if we could take this, and this is quite a bit of work here, if we could take this same expression and I could rewrite in polar form and polar trigonometric form, I could apply DeMoivres, and it's pretty quick. So rewriting it to polar form, however, has a little bit of work. So the first thing that we would do is we would look at this expression, negative 2 plus 2i root 3. And I'm going to rewrite that as negative 2 plus 2 root 3, and then the I is not under the radical, so be clear on that. So this would be x plus yi. And then from here, the first step I'll do is I'll graph this. And again, this is from a previous section where we learned to convert these. So the x value is a negative 2. The y value is a positive 2 root 3. So it's this point right here. So I'm in quadrant 2. So that's what I need to know from this step 1. Step 2, I need to find the radius. And radius is the square root of x squared. And again, that has to be in parentheses. 2 root 3 quantity squared. So I have r equal 4 plus 2 squared is 4. Root 3 quantity squared is 3. 12 plus 4 is 16. Square root of 16 is 4. So r equals 4 here. Last step, I need to find theta. So tangent theta is going to be y over x, so 2 root 3 over negative 2. This simplifies to a negative root 3. So from here I need to figure out, okay, where does tangent, and I'm working in quadrant 2 up here, so what angle has a tangent of a negative root 3 in quadrant 2? Well, that's going to be a multiple of pi over 3. So theta in this case, and again we need to be in quadrant 2, is 2 pi over 3. And that's 120 degrees, because we'll probably be working in degrees with this problem. So you can work in radians as well, but I think that it'll probably be easier to work in degrees, and I think most of your My Math Lab homework in this section does have you working in degrees, so we'll stick with degrees here. So if I were to rewrite this into its polar form, it would look like r, which is 4 cosine of 120 degrees plus I sine 120 degrees. Now we can use DeMoivres because I'm taking this value and I'm squaring it. So when I square it, I'm going to put curly braces around this because I'm squaring the whole thing, that's not the 4. So this ends up looking like 4 squared cosine of 120 degrees times 2 plus I sine 120 degrees times 2. And you're thinking the other method was shorter, but we'll see something, we'll come full circle at the end and it'll be equivalent, and then I'll show you why this is a better approach to use for some different types of problems. So 4 squared is 16. Then I have a cosine of 240 degrees plus I sine 240 degrees. Now we just go ahead and simplify this. Cosine of 240. 240 is in quadrant 3, so it's going to have a negative cosine. 240 is in quadrant 3, so it's going to have a negative sign as well. So 240 is a multiple of 60 degrees, or pi over 3. The cosine is 1/2. And then the sine would be square root of 3 over 2, and I already took care of the negative and positive part. So now I take the 16 and I distribute it here and here. So I end up with negative 16 times 1/2 plus I, the sign can go away here, sorry about that, I already took the sign of it, plus I times 16 times negative square root of 3 over 2. So I have a negative 8 here plus, let's see what we can simplify. Actually, that would be a minus 8 square roots of 3i. So I get the same answer as I did up here, I hope. Yep, negative 8 minus 8 root 3i, 8i root 3. So you might say, well, I think the first approach to finding this expansion was much faster, and you're probably right about that. Everything in green was the first approach, everything from the blue down is the second approach. And when you were just squaring something, you're absolutely correct. Maybe just going through and foiling it or using the box method is faster. However, what if we had a problem like 2 minus 2i to the 5th? This would mean I have to take 2 minus 2i times itself 5 times. Okay, and I'm not going to do that here because if we did, it would take a long, long time and the lecture would get very long. The point being, we don't want to do this. I would have to FOIL this one, FOIL this set of 2, multiply those 2 together, and then multiply that times 2 minus 2i. It would really get out of hand. And we might not be able to use the FOIL method on all of it. At some point we might have to use more something like the box method or the stack method. So this is where DeMoivres really shines, is when we have large powers right here. So let's go ahead first of all and convert to polar form, and then we'll apply DeMoivres. Okay, so converting this to polar form, the first step that we're going to take is to graph it and figure out which quadrant we're in. So if we graph this, I'm going to go 2, minus 2. So I'm in quadrant 4. So again, the 2 and the minus 2 come from right here. X is 2, y is negative 2. Second step, we're going to find r. r is the square root of x squared plus y squared. 2 squared plus a negative 2 squared, and again put parentheses around that negative sign. 2 squared is 4, 4 plus 4 is 8, so this is the square root of 8. But 8 has a factor that's a perfect square, so this is simplified to root 4 root 2. And the square root of 4 is 2, so r is 2 root 2 here. Third step, we want to find theta. So we use tangent theta equals y over x. Y in this case was negative 2, x is 2, so I have tangent theta equals negative 1. Well, that's going to be a multiple of pi over 4, but it has to be in quadrant 4. So I think that's going to be 3 pi over 4, 4 pi over 4, And again, I'm thinking radians here. So here's 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So theta would be 7 pi over 4. And again, we're probably going to be working in degrees a little bit easier here. So if we do that conversion, this is 315 degrees. Okay, so polar form then would be r, which is 2 square roots of 2 cosine of 315 degrees plus I sine of 315 degrees. Now what I want to do is I want to take this to the 5th power. Now why the 5th power? Because that's what our directions were, is right up here to the 5th power. So again, we'd have that 2 square roots of 2 cosine of 315 degrees plus I sine of 315 degrees, and all of this is going to be raised to the 5th power. So now we can apply DeMoivres. And again, this ends up making the problem easier for these higher powers. So this will look like 2 square roots of 2 to the 5th. Then I'll have cosine of 315 degrees times 5 plus I sine 315 degrees times 5. And that looks like a 0.5. It should be a times 5. Put it up here. So I have 2 root 2 to the 5th. So this would be 2 to the 5th times the square root of 2 to the 5th cosine. Now cosine here, I'm going to have 315 degrees times 5, so that's 1,575 degrees, plus I sine 1,575 degrees. Now we just have to continue to simplify this. So 2 to the 5th is 32. Now root 2 to the 5th. Well, root 2 to the 5th would be root 2, root 2, root 2, root 2, root 2. Well, this would be root 4. This pair would be root 4. And this one is just kind of off by itself. The square root of 4 is 2. Square root of 4 is 2. 2 times 2 is 4 root 2. And there's a lot of different ways you can do that. I think this is probably the easier approach to kind of visualize what's going on there. Now, 1,575 degrees. Let's figure out what's going on with that. Well, that's multiple turns around the unit circle. So what I need to do is I need to figure out how many times it turns around the unit circle, and then I need to figure out where it lands and then work with that angle. So let's look at 1,575 degrees. So what I want to do is I want to subtract 360 as many times as possible until I get down to an angle that's less than 360. So this subtracting one time would be 1215. Subtracting another time from there, subtracting 360 would be 855. So we definitely have some more spins around the unit circle here to go. We are going to do in minus another 360, which is 495, minus another 360 is going to leave us at 135 degrees. So that's what I can do up here, is I can rewrite this then as the cosine of 135 degrees plus I sine of 135 degrees. Because what happened here is that 1575 as I spun once around the unit circle, I went around the unit circle again, one more time, and that final time I ended up here at 135 degrees. So saying the cosine of 1575 will give you the exact same value as the cosine of 135. The cosine of 1575, you spun around the unit circle more than once. So the location at the end is the same, but the amount of rotations to get there was different. But you should just be able to substitute in the same value. So 32 times 4 would be 128, square root of 2. The cosine of 135, so this is quadrant 2. Quadrant 2 cosine is negative, so this would be negative square root of 2 over 2. Sine of 135 in quadrant 2 is positive, so this would just be square root of 2 over 2, and I don't need the sine in there because I already took the sine. And then we'll go ahead and take the 128 root 2 and we'll distribute to both terms. So I'll have 128 root 2 times negative root 2 over 2 plus 128 root 2 times I square root of 2 over 2. So canceling, 128 divided by 2 is 56, or wait, 64. So I'm left with 64. Root 2 times root 2 is 2. Negative I sign out front. 2 goes into 128 64 times. So this is root 2 times root 2 is root 4, which is 2. So 64 times 2 is back to 128i. So I ended up with negative 128 plus 128i is the expansion here. So that's a little less work than going through and multiplying this by itself 5 times, like we would have had to do from up here. So DeMoivres makes this pretty straightforward. And there's some work involved, but it's a very quick way to do these types of problems. Let's go ahead and look at one that is given to us in polar form for a change. Everything we've had to convert to polar form so far. So let's go ahead and take the square root of 6. And this is going to be given to you in that shorthand notation, the cis 120 to the 4th power. So the first thing that I'm going to do is I'm going to rewrite this excuse me, in its long form because I think it's a little bit easier to work with. So I have root 6 cosine of 120 plus I sine of 120. And again, curly braces because all of this is raised to the 4th power. So this is going to look like root 6 to the 4th. Cosine of 120 times 4 would be 480 degrees plus I sine of 480 degrees. Now root 6 to the 4th, that would be root 6, root 6, root 6, root 6. This would be the square root of 36, or just 6 eventually. So this boils down to just 36. Now cosine of 480. 480 degrees is going to be one full spin around the unit circle. That brings us to 360. And then we have to figure out how much further we're going to go. And it looks like we're going to go out to about 120. So the thing that we could look at here then is this would be the cosine of 120 plus I sine of 120. The amount of rotation is different, but the final resting spot is the same. The terminal side of the angle is the same. So cosine of 120, second quadrant, is going to be negative. So cosine of 120 is going to be a negative 1/2 plus I. Sine of 120 will be positive in the second quadrant, square root of 3 over 2. So I have 36 times a negative 1/2 plus 36i times the square root of 3 over 2. So this would be a negative 18 plus 18 root 3i. So again, negative 18 plus 18 root 3i. Now sometimes you'll see this written as 18i root 3, just to make sure that that I doesn't look like it's under the radical. If you leave the I out on the end, just make sure there's no question that it's not under that radical, because if it's not clear, it's wrong. Okay, you have to be very clear about that. So we've looked at expansions here for all of these complex numbers, whether they're given to us in rectangular form and we convert to polar and apply DeMoivres, or they're given to us in polar already and then we apply DeMoivres. What we're going to look at now is to continue to use DeMoivres, but for a different application. We're going to use DeMoivres to find roots. Now roots mean basically solutions, meaning if I plug this in, what am I going to get back out? Do I get a solution or not a solution? So once I plug it in, I would get basically 0 back out if you plugged it into both sides, or I would get an answer that works. Okay, so let's go ahead and look to see how we apply DeMoivres in that sense. So for this first problem, again, I think it's better if we just look at the problems here. Find the cube roots of negative 64i. So the important things here are cube roots, so this is important, and this negative 64i. So what we can start with here is we can look at this and think, okay, cube roots. That means there must be 3 of them. Okay, so when we get done, we should have 3 answers here probably. So to get started, what we want to do is we want to take this and convert it to polar form. So we want to convert negative 64i to polar form. Well, x plus yi would be 0 minus 64i. So x would be 0, y would be a negative 64. So 0, not moving off the origin, negative 64 we'll say is right here. So this is that vector that we're looking at. So I'm not in any particular quadrant. I'm in between quadrant 3 and quadrant 4. That's kind of the important thing to think about here. So I need to find out what r is. Now r is going to be easy. It's just going to be 64 here. So this is my first step, is to graph. Second step, r would be the square root of a negative 64 squared plus 0 squared, which is just 64. And then theta, I would do tangent of theta is y over x. That'd be negative 64 over 0, which is undefined. Well, I could use pi over 2 or 90 degrees, but really I already know where I'm at. I'm down here in between the 3rd and 4th quadrants, so theta would have to be 270 degrees or 3 pi over 2. So the next thing we're going to do is we're going to rewrite this in polar form. So the polar form is going to be r, which in this case was 64, cosine of 270 degrees plus I sine of 270 degrees. Okay? Now the key to this is to match this up with DeMoivres. So DeMoivres said, okay, r to the n cosine n theta plus I sine n theta. Now we're talking about cube roots here, and because we're talking about cube roots here, I can change this n to a 3. So this would be r to the 3rd cosine of 3 theta plus I sine of 3 theta. So we can see right away that if I take this 64 and rewrite it, that would be 4 cubed cosine of 270 plus I sine of 270. So if we match everything up here, r is equal to 4. I can see that from right here. I'm going to write that again down here. And then this tells me that 270 is equal to 3 theta. But this is going to happen every time I spin around the unit circle another 360 degrees. So k stands for any integer, meaning I could spin around once, twice, 3 times, 4 times, etc. So what we're going to do now is solve for theta. And then we'll table this and we'll figure out different angles here for different values of k. So divide through by 3, and I get theta equals 27 divided by 3 is 90 plus 120 degrees k. So this is what I'm going to want to table. So I'm going to choose different values for k, and then based on these different values for k, I'll plug them in and figure out what my angles are here. So k equals 0, k equal 1, k equal 2, k equal 3, and basically I'm going to keep going until I hit a k that when I plug it in I get something out of the one full spin around the unit circle, because once I hit that one full spin, it's just going to start repeating itself over and over again. So if I plug in k equals 0 here, I get 90 degrees. If I plug in k equal 1, I'll get 90 plus 120, which is 210 degrees. And if I plug in k equal 2, I'll get another 120 degrees basically. And so I end up with 330 degrees here. Now I'm going to go one more 120, and I get 450 degrees. And I always like to go one more spot until I make sure that I'm over the 360 mark. And then these will be what I use for my solutions. Okay, so for my solutions, what I do is I plug this into the general form of r to the n cosine theta plus I sine theta. So what this ends up looking like, sorry, this is just r, not r to the n. So r was equal to 4, so my first solution would be 4 cosine of 90 degrees plus I sine of 90 degrees. Now these are in polar form. You could convert these to rectangular by finding the sine and cosine of 90 degrees and then distributing the 4. This would be 4 cosine of 210 degrees plus I sine of 210 degrees, cosine of 330 degrees plus I sine 330 degrees. So these are my roots, or my solutions, and these are in polar form. I could convert them to rectangular form as well. Now from here, if I ask for finding cube roots, I should be able to see that I have 3 of these, so these are my 3 cube roots. Now if you wanted to, you could plug these back in and plug them in and see, are these the actual cube roots. Now let's go ahead and look at graphing these as well. These are vectors. Whoops. So I'm going to look at the one that's 90 degrees, so this is 4 units out. So there's one here. Okay, and then I also have another one at 210, so that would be here. This is 90 degrees. We'll call this 210 degrees. And then I have another one at 330 degrees. So 330 degrees would be right here. Now this is 4 units out. It's easy to see on this one because I went up to the 4, but these are also 4 units out. So if you looked at this, and this is not going to go well, but there's a circle here of radius 4, so you have to use your imagination that that's a perfect circle. So that's what we do to find the cube roots. Kind of using DeMoivres, you match those values up and you kind of work a little bit backwards to figure out what those are. These are pretty straightforward problems as long as you know your unit circle and you can follow the process. Now you won't always be finding cube roots. Most of your problems are cube roots. I'm not sure why they always do cube roots, but they do. But I want to make sure that we do one that's not a cube root, so when you run across that in your homework, it's familiar to you. So I'm going to do one where you're looking at square roots. Okay, so for this one, find and graph the square roots of negative 144. Negative 144. Okay, so when we get to the end, we're going to have 2 solutions in polar form. And what I would like to do is I would like to convert these, and when I convert these, we're going to convert them to rectangular form, and you'll probably see something that looks pretty familiar. So there are faster ways to do some of these. This is more of a demonstration on how, when we work through one of these problems, that it would work for this simple problem, and it would also apply to more complex problems. So to get started, we want to take negative 144 to polar form. And of course, polar and trigonometric form means the exact same thing, so you can use those interchangeably. So if I do this, I have x plus yi. So x in this case is negative 144 because it does not have a factor of I. So x is negative 144, y is equal to 0. So now we want to graph this, and we're going to be right in between 2 quadrants. So negative 144 we'll say is right here. So I'm going to be right in between quadrant 2 and quadrant 3. Okay? So that's my first step. Second step is I want to find r. You can apply x squared plus y squared square rooted, and I will get 12 back out of that. Or sorry, 144 out of that because I have a 144 here. So double check that, and then step 3 is I want to figure out what theta is. Well, I can already see what theta is. It's right here. I could apply the tangent, but I can see that it's going to be 180 degrees. So the polar form is going to be r, which is 144 cosine of 180 degrees plus I sine of 180 degrees. And then what we do is we look at this and we match it up and we say, okay, this is square root, so we want this to match with r squared cosine of 2 theta plus I sine of 2 theta. So if r squared is 144, r would be 12. And then 2 theta would be equal to 180. So r is 12. We can see that right now because we have 12 squared. So cosine of 2 theta is cosine of 180. So 2 theta equals 180 degrees. And this is going to happen every 360 degrees around the unit circle. So 180 divided by 2 is 90 plus 180 degrees K. Now next what we'll do is we will create this table. Now square roots to me mean I better have 2 solutions here, but let's find that out for sure. If it was cube roots, I'd look for 3 solutions. So I'll plug in k equals 0, k equal 1, k equal 2. If I plug in k equals 0, I get 90 degrees. If I plug in k equal 1, I get 180 plus 90, which is 270. And if I plug in k equal 3, I get 180 times 2, which is 360, plus another 90 would be 450. And again, I've gone one full spin around the unit circle, and I always make sure I find the one that's beyond, so I know that I'm done checking, and I will use these for the solutions. Okay, so next we're going to go ahead and write out these solutions. That would be r, which we found out was 12, cosine of 90 degrees plus I sine of 90 degrees. That would be one solution. And the other solution would be 12 cosine of 270 degrees plus I sine of 270 degrees. So those are my solutions. These are in polar form. Now, what if we kept going and we converted these to rectangular form? Well, that would be cosine of 90 is 0 plus sine of 90 is 1 times I is I. So this would be 12i. Cosine of 270 is 0. Sine of 270 is negative 1. Negative 1 times I is negative I times 12 is 12, negative 12i. These are in rectangular form. And again, these are in polar trig form. Now, I don't know if anybody else thought about this, but wouldn't this just be the square root of negative 144, which is the square root of negative 1, square root of 144. So this would be I times square root of 144 is 12, and I have positive and negative roots. So this would be plus or minus 12i. That seems a little shorter than all the work we've done. But again, this is just an example in the easy case that it matches up with what we would expect. And so when we get to a more difficult case, it will work just as well. Now, it doesn't matter to me what method you use, so if you came across this on an exam and you're thinking, this would be pretty quick, I'm fine with that. Okay, unless it says you have to use a particular method, you can choose the method that you want to use. Okay, last type of problem we're going to be looking at. We're going to actually be looking at an equation. So here we're given the job to find all complex number solutions. To the equation x cubed minus 512 equals 0. Okay, so x cubed minus 512 equals 0. So from here, what I can do is I can go through the same steps I've just done before. I'm going to write this in polar form, and then from polar form I will apply that kind of reverse DeMoivres and find my solutions. So to get started, let's go ahead and add the 512 across. And then what I can do from here is I can figure out what this is in a rectangular form. So I'm going to take 512 plus 0i basically. So this would be x plus yi. So x is equal to 512, y is equal to 0. So if I were to graph this, I'd be out here at 512 units. Y would equal 0. So I'm in between quadrant 4 and quadrant 1. Okay? So second step, or first step is graphing. Second step is to find r. In this particular case, r is going to be 512 because I'm just right on that quadrantial line. If you want to plug it in and figure that out, you can. And I can also see from this quadrantial line that theta is equal to 0 degrees. So I can take this and rewrite it in polar form. So polar form again would be that r, 512, cosine of 0 degrees plus I sine of 0 degrees. Next we're going to go ahead and see if we can match this up with r. Now this is find all complex number solutions. This is to the third power, so I'm going to use r cubed here. Cosine of 3 theta plus I sine of 3 theta. So we need to figure out what the cubic root of 512 is, and 8 cubed would fit the bill for that. So again, this would be the cosine of 3 theta plus I sine of 3 theta. So r is equal to 8. So what I do then is I take this 3 theta, I set it equal to 0 degrees, and I say, okay, this is going to happen every 360 degrees. I'm going to hit that spot again. So I divide both sides through by 3, and I get theta equals 0 degrees plus 120 degrees K. Now I don't need the 0 degrees there, but it's just going to kind of help me remember that I'm starting at 0. Now we're going to go ahead and plug in values of K. So K equals 0 would be 0 degrees here. Next we would go ahead and go with our next one. If I plug in K equal 1, I'd have 120 degrees. 240 would be my next one. And then I'd hit here at 360, but 360 starts me all over again at 0, so these I will use for my solutions. So I'm going to write my 3 solutions, and again the 3 comes from the fact that this is a third power, in polar form. And I can also write them in rectangular form as well, but I'll just write these in polar form for now. So r is 8 cosine of 0 degrees plus I sine of 0 degrees would be 1. Next would be 8 times the cosine of 120 degrees plus I sine of 120 degrees. 8 cosine of 240 degrees plus I sine of 240 degrees. So these are my 3 solutions. Now think about this. Convert these to rectangular form as well. That would be a problem that would be for the handwritten homework and on an exam. So make sure you know how to convert between polar / trig and rectangular form and be able to work with those back and forth. So make sure DeMoivres is on your note card. If you have any questions while you're working, please let me know. It's best to send a screenshot of the problem so I can see what any conditions are that you're working with, such as restrictions. And then also send me a screenshot of your work so I can see maybe where things went a little bit wrong for you while you were working. As usual, if you have questions, let me know. Don't hesitate to ask, and good luck.